So today I'm going to try to explain how this equation was was derived and how we can use it. The reason why is because one property of this equation actually confused me quite a lot. So CV is basically the heat capacity for constant pressure, constant volume. This is V. It's kind of ugly. V. Oh, it's even ugly. And the other one is under. So this one is const volume. And this one is const pressure. And the end formula is this right here and this right here. And I'm gonna deduct it. So to get the this is this right here is based on definition. So the definition of heat capacity is the energy required to create temperature, a change of temperature. So in other words, change of energy is over change of temperature equals heat capacity, and therefore um, therefore this right here is basically based on definition. But one thing we need to know is it is not we are not sure if u is as a function of only time. Therefore, this is why this this delta is used instead of the one that we like, this, because once we have this, we can just take the integral and get get the value using integration. So the first reason why u equals uh is function of temperature is because um of an experiment. So if you can go Google um the Joule, basically the scientist Joule, he had an experiment that concluded that this is true. So now we can for sure write the constant volume as d u dt right here. Um, but this is only for constant volume because of the experiment. It in the experiment, the condition is the volume is constant. How do we prove that this is going to be also dHdt? Then we go back. We go back to our ideal gas law. Our ideal gas law stated that enthalpy equals U plus PV. Now, this term has nothing to do with temperature. Well, it does, but it's, you know, it's this. Ideally, we want the whole right hand side to be a function of temperature. But with ideal gas, we know that um, this equation is also true for ideal gases. Therefore, we can replace PV by RT. Now, this is what we use to, because this is a constant. This is a constant. And U is a function of T. And then plus essentially a constant plus temperature. Then what does this mean? It means enthalpy is a function of time. Now we can do this. Now this is finally true. D D H D T. And and this is perfect for us because now we have what we have. We have CV equals d du dt from the experiment. We have CH equals dh dt from the derivation up here. Now we just take the integral. Well, there's one more step. We gotta do this, move it a bit, do a little algebra, dt, and now we take the integral, and it basically says, um, let's just say 1 to 2. This makes it so that u2 minus u1 equals um, CV, okay, equals this. Now, usually in the examples, we can just use this as constant because since CV is a constant of temperature, but it doesn't changes that much, and basically this one is the same process. So do the same process, and you will get U H2 minus H1 equals CP dt. But the question that I had, the biggest question was that why can we use CV, CP even when it's not constant volume nor constant pressure? But from all of our equation derivation, it doesn't. CV is not a function of volume, nor is CP a function of pressure. It's simply just a state. So that troubled me a lot because I'll see a lot of question that says, oh, I have the temperature change, right? And if you have temperature change, then you can basically say, oh, the temperature change is gonna we can use the temperature change to calculate CP, for example, times the temperature change, right? Even when the process is not constant pressure. Um, so the answer to my own question is basically CP is not a function of pressure. So it doesn't really matter. It's more of like using the two different state to calculate the difference in enthalpy.